Now we're going to look at hydrohalogenation and use it to illustrate some regiochemical considerations. So let's say we do the following reaction. We have an alkene and an HX molecule. Okay. And there are two possible addition products, and they differ where the halogen adds. Okay, so we can get this one where the halogen adds on the more substituted carbon, or we can get the one where the halogen adds on the less substituted carbon. And these are called Markovnikov and anti-Markovnikov. And it turns out that we can control whether we get Markovnikov addition or anti-Markovnikov addition. And that depends on the mechanism we go through. First, we're going to look at ionic mechanism. Which gives us the Markovnikov addition product. So let's draw out the mechanism. Here is our alkene and our HX molecule. First step, the pi bond acts as a base, abstracting a proton from the halo acid. And this is going to give us a carbocation. Now we can have a carbocation in a more substituted position or a less substituted position, depending on which side of the double bond the hydrogen adds to. And since a more substituted carbocation is more stable, the hydrogen is going to add to the less substituted position, giving you this carbocation. So that's where our hydrogen adds, and we get a tertiary carbocation, which is more stable. Note here that if the hydrogen added to the more substituted position, then we get a secondary carbocation. And then in the second step, we get nucleophilic attack from the halide ion that's produced in that first proton transfer step, and it's going to attack that carbocation. And there's our product, and that is Markovnikov. So let's look at the thermodynamics, the kinetics of this, really. Okay. So we're starting out here with our alkene. And when it acts as a nucleophile, when it acts as a base and abstracts the proton, the transition state where the carbocation begins to form in the more substituted position, that is shown by the red line, that gives us a tertiary carbocation. That's going to be at lower energy than the one where the hydrogen is added to the more substituted position, giving us a secondary carbocation. Thus, the tertiary carbocation forms faster, and it dominates the mechanism. This is why, with an ionic mechanism, you get the Markovnikov product. Now, this is just a preview because we haven't talked about radical chemistry yet, but if you add a peroxide, you get the anti-Markovnikov product, and this is because it goes through a radical mechanism. as opposed to ionic. No charged intermediates are produced, and so instead of 2 electrons in a curved arrow, we use a fishhook, right, which is a curved arrow that looks like that, and that represents 1 electron instead of 2. So our peroxide is going to look like RO to OR. And in the first step, it's going to do homolytic cleavage. And this is going to give us 2 OR radicals. Right, and you can see those are radicals because they have an odd number of electrons. So that homolytic cleavage is the first step in the radical mechanism. The second step, we have one of these RO radicals attacking or performing hydrogen abstraction on our halo acid. Okay, so you need 3 fishhooks for this. That's forming a bond between the RO and the H to make an alcohol. And then we're also going to get a halogen radical, because one of the electrons in that bond ends up on the X atom. So we get ROH, that's our alcohol, plus halogen radical. Now for step 3. So we have our halogen radical that was produced in step 2, and we have our alkene. Okay, and we need 2 fishhooks here, or 3 rather. That's the formation of the bond, and we're also going to have a fishhook like that. Okay, and this is a tertiary radical. This is more stable than the secondary radical we would get if the CX bond was formed on the more substituted carbon, and this is why we get anti-Markovnikov addition instead of Markovnikov addition. In step 4, our tertiary radical reacts with another molecule of the acid. This gives us our final product. Right, it gets rid of that radical, and we get a new halogen radical. This can react with more of the alkene. So this is what we call a chain reaction. So here we have a hydrohalogenation question, and we're going to try to predict the major product. So here we go. We're reacting an alkene with hydrochloric acid. Essentially, there are 2 products that we could get. That one where the Cl adds to carbon number 3, or this one, where the Cl adds to carbon number 2. But in this case, we can't apply Markovnikov and anti-Markovnikov because both carbon 3 and carbon 2 are equally substituted. We could predict a 50-50 mixture here. Despite the fact that we would anticipate seeing the Markovnikov product. Here's another case to consider. This alkene is disubstituted on the left side and monosubstituted on the right. So, our two possible products there's the Markovnikov product, and the anti-Markovnikov product puts the chlorine over here. And we would, of course, expect the Markovnikov product to be the major product in the absence of a peroxide. Oops, it looks like I lost a methyl group here on both of these. It should be there and there. Sorry about that. Okay, now, if we wanted to get the anti-Markovnikov as the major product, we could start out with the same reactant, and we could use hydrochloric acid and a peroxide, and just put ROOR underneath your arrow, and this would give us the anti-Markovnikov. And you know it'll be anti-Markovnikov because of the presence of a peroxide. Okay, so that's that for hydrohalogenation.